Hello again. This is Math 1120 coming to you from the College of DuPage, and the title of this lecture is Interventions for Density, Pressure, and Logarithms. As always, be sure to be an active learner as you watch this video. A steel wrench and a steel nail show that they have different masses. This has a larger mass than this, but they have the same density because the wrench and the nail are both made of steel. They have the same density, mass per unit volume. The definition of density. We use the Greek letter rho, looks kind of like a P, for density. If a mass M of a material has a volume V, then its density is rho equals mass per volume, and that means its units in the SI system would be kilograms per meter squared. This table shows some densities of some common substances. So you see air has a density, various liquids have a density, solids have densities, and different gases have different densities. You see that gold has a very high density. That's one of the reasons I think people think it is valuable. And platinum, you can see, has even a higher density than gold. I think a platinum card is better than a gold card. Anyway, and you can see how dense some of the astronomical things are, the neutron star and so on and so forth. So you have these numbers, and these are units of kilograms per meter squared, and to obtain the densities in grams per centimeter, simply divide by 10 to the cube. That actually is a nice dimensional analysis problem for you to think about that one. Here's an example. This coffee drink was made by using liquids of different densities in a steady hand. The liquid with the highest density was poured first, and the lighter ones were poured later, and they don't run into each other because they stay in their own lanes. Aside from nice coffees, density measurements are an important analytical technique. For example, density can be used to determine the concentration of sulfuric acid in a car battery, or as a monitor of the ethanol content in the fermentation processing of alcoholic beverages such as beer and wine. So here's a test your understanding. If you cut a block of modeling clay in half, the density of each half is blank. You have to pick one of these. The density of the original block. Well, because the clay in the block is a homogeneous, that means it's the same throughout material, its density, mass per unit volume, is the same for the pieces of any size. Therefore, the correct answer is B. We could also do a numerical problem, and let's do one. Let's begin with a simple calculation of the weight of air using density. So we want to find the mass of air and its weight in a living room that has a 4 meter by 5 meter floor and a ceiling that is 3 meters high. 3 meters is between 9 and 10 feet, so that's a pretty high ceiling. What are the mass and weight of an equal volume of water? That's a secondary question. So first thing we do is we draw a picture, and we find that this is 3 times 4 times 5 is 60 cubic meters is what we have. Now the air has a density of 1.2 kilograms per cubic meter, so that means the mass is equal to rho times V. That is 1.2 kilograms per cubic meter times 60 cubic meters is 72 kilograms. Now that's the mass, but the weight is going to be, the W is equal to m times g, the acceleration due to gravity. So that is 72 times 9.8. You check the units, and that's going to be newtons, so that is 710 newtons. Now the density of water is 1.0 times 10 cubed kilograms per cubic meter, a much bigger number than this. Thus, the mass of a volume of water that would fill the room is m is equal to rho times v. This is the big mass number times the same volume number. 60 meters cubed is 6.0 times 10 to the fourth kilograms. That's its mass. So the weight is that times 9.8, and that is 5.9 times 10 to the fifth newtons. Here's a practice problem for you. What volume of water would have a mass equal to the mass of air in the room? And there's an answer for you. We now turn our attention to pressure. The pressure is the magnitude F perpendicular, that's F sub, little symbol like that, F perpendicular, it looks like this, of the force exerted on a surface divided by the area of that surface. So pressure is equal to force perpendicular divided by A, and that means that force perpendicular is pressure times A. And here's the picture. And if you have an F going at an angle, so here's your area, you have a force going at an angle. Well, force perpendicular is this, so that would be the sine of theta times that if this angle were to be theta. So it's important to remember this is the force perpendicular. Okay, the units are going to be newtons, that's forces per. Area is newtons per meter squared. Now we have a name for that. That is called a Pascal, or PA. So this is Pascal in physics class, not Pennsylvania. Now pressure is a scalar quantity, and 1 Newton per meter squared is equivalent to 1 Pascal, which is PL, and that's often the unit that we will use. There are related units that are used in meteorology and things like that. We're not really going to be doing much problems with that. If we ever do a problem with that, we'll define that within the problem. Okay, let's look at a room full of air again. And we want to calculate the force that the atmospheric pressure produces on a surface. So consider the room we talked about before, and that was the one we just talked about. What is the total force on the floor due to the air above the surface if the air pressure is 1 atmosphere? Now 1 atmosphere is 1.013 times 10 to the fifth Pascal. So here's what we're going to say. The force perpendicular is equal to the pressure times the area. And remember that this floor was 4 times 5, so its area was 20 square meters. So I take this number here, the pressure of an atmosphere, times that. I get that this is 2.0 times 10 to the 6 newtons. And that's actually quite a bit of weight. 10 to the 6 is, that's 2 million newtons. Here's a practice problem if you want to practice these kind of considerations. Now, one of the big important things that we're going to talk about pressure, we could talk about many things, but we're going to talk about a thing called Pascal's Law, and the unit of pressure was named after this same Pascal. And here's what he said. Pressure applied to an enclosed fluid is transmitted undiminished to every portion of the fluid and the walls of the containing vessel. The pressure depends only on the depth, and the shape of the container does not matter. So that says if your liquid or your fluid is not compressed, then the pressure is going to be the same throughout on all the boundaries and everything else. Let's talk about what that means in the context of this. So suppose you have a little disc and you're putting a pressure 1 on that. That causes a pressure. It goes through, but now what you have is you have a big volume here, a big area, but it's the same pressure. And pressure, the force is pressure times area. So you're putting this pressure in, it goes and it does this. Well, what really happens is that F1 over A1 is equal to F2 over A2. Or F2 is equal to A2 over A1 times F1. And so you can do problems with this, and what really happens is This is called a hydraulic jack. The hydraulic jack is a force amplifying device with an amplification factor equal to the ratio A2 to A1. So you see, if A2 is much bigger than A1, you can lift a heavier car using this. Dentist chairs, chair lifts and jacks, some elevators, and hydraulic brakes in your car all use the same principle. Okay, let's see how Pascal's law can be used to amplify a force. So suppose the hydraulic lift, the one we looked in the previous picture, has a cylindrical piston with radius 5 centimeters, and the large piston on the other end has a radius of 20 centimeters. The mass of the car placed on the larger piston is 1,000 kilograms. Assuming the two pistons are the same height, what force must be applied to the small piston to lift the car? And how far must the small piston move to lift the car through a height of 1/10 of a meter? Okay, well, we just can use this formula that we have. F1 is equal to A1 over A2. And these areas are going to be circles, pi r squared, pi r squared. The pi's will cancel out, and you'll square the various things. And so you see that to lift the car, you have a force of 610 newtons, can lift a car that weighs 9,800 newtons. Now in part B, what we're asking is how far must the small piston move to move the car there? Well, the distance is going to be this ratio, and so the small piston would have to raise it. It would have to move further to do it. But you move further, but even though you move further, you don't have to push as hard. Another qualitative example comes from snowshoes. If you were just trying to walk on the snow, you might slip in, but if you wear snowshoes, you can walk on the snow. Well, the reason is that this increases the area of your foot, so your weight is the same force pushing down, but now it's spread over an area, so the pressure is less, and you can walk on the snow. Last but not least are logarithmic and exponential functions. Exponential functions and logarithms are used for many natural phenomena, such as radioactive decay, where the rate of increase or decrease of a quantity is proportional to the current value of that quantity. We also work with exponential growth and decay in the study of electrical circuits, and I had you watch a video during the first part of this course about exponential growth. So we're going to encounter two types of logarithms. Actually, in a physics book, you encounter two types. In just this course, there's only going to be one type, and we're going to talk about the common logarithm, and the common logarithm is the base 10 logarithm. And that's written as log. So the base 10 logarithm is of a number y is the power to which 10 must be raised to obtain y. You have to think about that a little while, and I'll show you an easy way to remember that. But that means that y equal 10 to the log y. So you see this is an inverse function of 10 to the x, is the log x. Logarithms behave kind of like exponents, and those that will help you remember the properties of exponents we'll talk about in a bit. For example, 10 cubed is 1,000, so the logarithm, the common logarithm base 10 of 1,000 is 3. Most calculators have a key, and I'll show you that. Sometimes we're given the logarithm of a number and asked to find the number. That is, if log y equals x, and that's logarithm base 10 of y equal x, and x is given, what is y? Well, to solve for this, we write an equation in which 10 is raised to the power equal to that side. For example, if we were trying to solve this one, log base 10 of y equal x, that would mean that 10 to the x equal 10 to the log y. but log y is y, so y would be equal to 10 to the x. Now y is called the anti-logarithm, and if you have log base y is equal to minus 2, that would mean that y is equal to 10 to the minus 2, and that is 1 times 10 to the minus 2, and that is going to be 0.010. The log of a number is positive if the number is greater than 1. Here's a graph of that, but it grows very slowly. You have to go up to 100 to get b to 2. You have to go up to 10 to be 1. The log of a number is negative if the number is less than 1 but greater than 0, and those are these numbers down here. The log of 0 or of a negative number is not defined, so we have this as the domain. And an important thing is the logarithm base 10 of 1 is equal to 0. Now, I'm not going to talk about the natural logarithm except to say don't use this, just use the log. This is an important function, but it's not something that we need to focus on now. Logarithms with any choice of base, including base 10, obey several laws. I'm writing this law because when students come into the Learning Commons, sometimes this helps them. And so this is a general principle. We've really already talked about it before, but it's worth saying again. The logarithm base a of b equals c, if and only if a to the c equal b. This is called the logarithmic form. This is called the exponential form. So a to the c equal b means logarithm base a of b equal c. There are some other properties. The logarithm of a times b is the logarithm of a plus logarithm of b, just like exponents. The logarithm of a divided by b is the logarithm of a minus the logarithm of b, just like exponents. And the logarithm of a to the n is n times log a, just like exponents. A particular example of this is the second rule, because the rule we talked about earlier, because the log of 1 is 0. Also, the log of 1 over a is the log of 1, which is 0 minus a, so that is the log minus the log of a. Now, you might say, well, we won't have to know these, will we? Yes, you will, because the logarithms will come up in upcoming section. Here's an example problem. This is where the buttons are on your calculator, and we'll review some of that during the VCM session. All right, so let's apply the logarithm rules to solve. 1/2 is equal to e to the minus alpha t, and you want to solve for t in terms of alpha. Well, look what we have here. We really have this form, don't we? We have e raised to a certain power is equal to b. So we can take the natural logarithm of both sides. We get the natural logarithm of 1/2. That's the logarithm of this side. And when I take the natural logarithm of this other side, I tear off the exponent, and I get minus alpha t. So that leaves us with minus alpha t is equal to minus ln 2. That means we can divide both sides by minus alpha, and we get t is equal to natural logarithm of 2 divided by alpha. I hope these interventions are useful, because these things will be coming up soon. In closing, now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now more than ever, take care of yourself and of each other. We're all in this together. May God bless you all.